Hello dear friends and welcome to another electronics tutorial. Today we will be discussing capacitors. So capacitors are widely used in electronics. They are used in most modern circuits. Very hard to integrate them into integrated circuits. Usually the capacitors are placed outside. Mainly going into the function area of a capacitor, they are used to store charge and to isolate different signals from one another because the capacitor allows a signal to pass through it. So any signal source would pass from one side to another. As a structural design, the capacitor is formed out of two plates. So there are two metal plates separated by a dielectric. Um, any of the plates, so the dielectric can be um, either air, it could be even paper, or it can be, let's say, more modern dielectrics like ceramics and yeah, dielectric isolation or special substances used to create a dielectric here. Um, the main function, so the stored charge function works the following. So you have a power supply or power source. This supplies one of the plates with um, positive charge and the other plate with negative charge. And why do we use these capacitors for storing charge? As you are actually draining the battery just to store this charge in the capacitors. Storing the charge would allow a more stable voltage level. So, for example, if this power supply is quite noisy, because you have multiple capacitors in parallel on the input, and especially ceramic capacitors, which have a very a small ESRs or equivalent series resistor, they would stabilize this line quite well. So here, for example, if you have a 10 volt power supply and you have 100, let's say, millivolts ripple, so up on top of the 10 volts you have a small ripple, this would be uh, removed if you place multiple capacitors on this line. And this would be the stored charge would be the DC behavior for the capacitor. Regarding the AC behavior for a capacitor, in case, for example, here we would have a signal source. For example, could be even an audio source from an iPad or any audio signals. Then this would be isolated through this capacitor to, for example, an amplifier that you want, for example, to listen to music at home. This capacitor would create an isolation between the two circuits, but would allow the signal to pass from one side to another, and it would be either circuits would be able to function independently from one another. Going back a bit to the type of capacitors, there are tantalum, aluminum, ceramic, thin film, trimmer. From my experience, I recommend you use ceramic capacitors, even if you have to place multiple capacitors in parallel to get to the required capacity, because they have a very good ESR behavior for the capacitor. There are also aluminum capacitors, which are quite used. These have a higher ESR. The ESR, please imagine, is the equivalent series resistor. So it is like a resistor placed on this side of the capacitor that allows the charge to be stored less faster or slower. All capacitors have an ESR or equivalent series resistor, but if, for example, ceramic capacitors, this resistance is quite small and the charge is much faster stored on these plates than, for example, for aluminum capacitors. Going a bit forward to some of the parameter for capacitors, the capacitance is the main parameter for a capacitor. It's measured in farads. For this example, I took a 10 microfarad capacitor here just to get an overview. Tolerance is another very important parameter. So this is how much the capacitance may fluctuate. So for this capacitor with a plus minus 10% tolerance, it can fluctuate from 9 microfarads to 11 microfarads. And this is quite important when you are transmitting signals from this through this capacitor. Also the rated voltage. Rated voltage for this example, I've taken a 16 volt capacitor. So regarding the rated voltage, I can recommend that you do not exceed 80% of the rated voltage. So in this case, this quite small rated voltage of 16 volts, yeah, do not try to go above kind of 12.8 volts, because this would yeah, it would strain the capacitor a bit, and in time this would cause a failure. It's better to go if you have a circuit that has a higher output voltage or closer to 16 volts. Better to use a 25 volts or a 50 volt rated capacitor for your application. And again, the technology, in this case, the best one from, from my point of view is MLCC, so multi-layer ceramic capacitor. They are quite good. I use them also in power supplies, in audio amplifiers, and they are very stable, resistant to high ripple current. So you can only win with these types of capacitors. Here is a small picture with some type of capacitors. So there are some small ceramic capacitors here. There are also some electrolytic capacitors. What I would like to make quite clear, so it is very important for the electrolytic capacitors that you know where the minus is. So the minus is this, you can see an arrow here. This is the minus arrow indicating that this pin here is the minus connection, and this would be the plus connection. So here you can connect voltage, and here this should go to ground. And same here, so this is a 16 volts 100 microfarad capacitor. The arrow is pointing downwards. This means that this pin here is the negative pin, and this is the positive pin. If by any chance they are placed on the other side, it would cause it would cause this capacitor to explode. Also here you can see, so these are with terminals on opposite ends. With the terminals on the same end, which are more common, you can see here this is a 35 volt 4.7 microfarads capacitor. You can see the negative terminal is on this side here with this strip. You can see the strip here, it's indicating the minus value for this. If they are not polarized, then you have no indication on which side is polarized, or which side is the plus and which side is the minus. Going a bit forward regarding topologies. So as I said, you would for your circuit you may have different capacity needs just for filtering. If you place on the input, this is very common that more capacitors are placed in parallel. Also, they are very common. It is that, for example, you use a 10 decade um, um, drop. So for example, here you place 100 microfarads, then here you place 10 microfarad, then you place here 1 microfarad, because they would ensure different behaviors, also because of the ESR, and of course regarding the impedance, but we will discuss this a bit later. If we place them in series, it's same as for the resistors. So the total capacitance is 1 over the total capacitance is 1 over the first capacitance plus 1 over the second capacitance plus of 1 over the third capacitance, and so on and so forth. So to calculate this faster, the total capacitance is usually C1 times C2 times C3 divided by C1 plus C2 plus C3. And this is just for for speeding things up. Now, what is very fundamental from my point of view is that we also discuss how the impedance of a capacitor changes. So what is the impedance? It's the resistance of the capacitor at some frequency. If you're going into signal, the capacitor will act as a resistor, so it will allow signal to go through it, as I said, and this, according to this impedance, it will allow more or less frequency to pass through it. In this case, I have taken the 10 microfarad capacitor that we've been discussing previously, and then I have fixed frequency for the capacitor, so I'm supplying it at a 10 kilohertz sine signal, and the impedance is 1 over 2 times pi times the frequency of the signal that I'm injecting in the capacitor times 10 microfarads, which is the capacitance. And this results in 1.59 ohm, which is the actual, which would be the actual value for this component at the specific frequency. Okay, going forward, let me zoom out a bit. Going forward, I would like for us to look together on a simulation where we can discuss a bit more about the actual behavior and run some circuits so that we can better understand how capacitors work. Um, for this simulation, I'm going to use Cadence, Cadence ORCAD tool, and for this tool you can find it free license online, or you can yeah, if you're a student you can get a special student license. Okay, let's go to the simulation. So this is how ORCAD looks after you first open it. The first thing that you need to do is to start a new project. I'm gonna call this project Capacitors, and this will be Capacitor Bench. Okay, and then I'm going to create a blank project just in case. Now this is the main area where we will draw our schematic. On the right side are a list of libraries. If you do not see the libraries here, you can add libraries, but make sure that you are, for example, in the correct library for your software. And then you should see in the Spice, you can see a lot of libraries with components that you may need. Okay, so the first step is to see how a capacitor behaves. So then I'm going to take a VDC power supply. So this is a direct current, this is a DC power supply, and we said that we will try to supply this at 12 volts. Okay, then we are going to take a resistor because this is an ideal power supply, and the power supplies, all the power supplies have an internal resistance. I'm going to take this, I don't know, 500 ohm resistor to see how this would work out. Connect them. So for driving a wire between these two connections, you can always press W on the keyboard in OrCAD and you get the wire automatically. Yeah, and for the components, it's VDC for the power supply and R simple, R analog for the resistor. For the capacitor, it's C, and we go with C analog. We place the capacitor here. Let's go with a bigger one, just that we see the charging ramp, 470 microfarads capacitor. Okay, and for the ground, you need to press the G key on your keyboard, and then always use the zero cap sim. You will know it's the correct one when you have a zero here. And let's place it here. Okay, now W and placing the wires, W and placing the wires. Okay, going forward, now we're going to start the simulation profile. This is quite simple to do. Press the plus sign here. Let's create a simulation profile, sim1. Click enter, and now this is the simulation settings. So here are quite some important settings that you need to create. So first of all, let's run a time domain or transient simulation. Transient means that we would see how the circuit would react from the initial starting of the circuit, and then we would see how it would evolve for a certain period of time. Let's put here 10 milliseconds so that we end the simulation after 10 milliseconds, and then we can put a step size of 1 microsecond here. Okay, great. Now, one other thing we need to do is we need to put a voltage probe. Here are the voltage probes. These measure the voltage levels in different points on the circuit. Now we place the voltage probe on the capacitor just to see how this component charges. Okay, let's run the simulation and see. Okay, so it doesn't have a charge time. It has we we will need to add a switch, just that the stabilization time we have some stabilization time for the circuit. So the circuit runs the simulation as if the power supply is connected and starts from the situation where the power supply is connected, and this means that here you would see only 12 volts. You will not see the capacitor charging. It would start automatically with the capacitor charged. Now, in order to avoid this situation, we need to use a switch. So the switch has a set of parameters, but this one is the most important. So it's the closing time. Let me put value and name, and let's close this after 1 milliseconds. Okay, and let's put let's put the switch here between the power supply and the capacitor. Now we put the switch W for wire, and it should. Okay, so before moving forward with the simulation, we need to add one more thing to the schematic. We would need a load, because this is an ideal capacitor here, and being an ideal capacitor, it would have yeah, it would just charge instantly and would not have any load to drive. So for this, I'm going to use a resistor. In this case, I'm going to leave it at 1 kilo ohm resistor so that we can have some leakage current going through this resistor here. Okay, and let's run the simulation. Let me place a voltage probe here on the output so that we can see how the voltage is charging the capacitor. So let's see how this is looking. Beautiful. So we see here that before the switch is turned on, there is no voltage on the capacitor, and then the capacitor charges in about, so from 2 milliseconds to about 6.5 milliseconds. So this is give or take 5 milliseconds, it's fully charged as a capacitor. Another very important circuit, so the second feature that we have also discussed today is the ability for the capacitor to allow signal to pass through it. For this, we would need a sine or a signal source, which is vSyn from the ORCAD library. And let's create a quite small signal, so about 500 millivolts um, offset and 500 millivolts amplitude at, let's say, 10 kilohertz frequency, and for the AC signal also 10 kilohertz. Okay, so this is our sine generator, and with this sine generator I would like to pass through a capacitor and to a load. Let's put a also 1 kilo ohm load, it's okay. And then of course we would need a ground point, so G of course again, and we can select the capsim component. Let's put and connect everything with a wire with placing the W key, and then of course maybe increasing the capacitance here to maybe 10 microfarads would be also indicated so that we can better see how much this is going from one side to another. Okay, so let's see now if this sine wave passes through this capacitor to a resistor. Okay, also we will need a voltage probe here and the voltage probe. Let's put one voltage probe on the input, run the simulation. Okay, so now we see a beautiful 1 volt sine wave, and then let's create another plot window where we can see the output signal to see if this is working. So yes, after passing through the capacitor, you can see this beautiful one wave, and you can also see a dephase between these two, very small. Yeah, it's unnoticeable at this time, but you can see that the same signal passing through these two components. Okay, one is scaled at, yeah, one is at 0.5 and the other one has no DC component. Why? Because we have this isolation capacitor here. Great. One other component or circuit that is quite important to know in the beginning of the of our electronic journey is a signal divider. Signal divider is a circuit that does and divides the signal into two, and it's quite similar to a voltage divider done with a resistor, but in this case it's done with two capacitors. So let's look how this is looking after. Oh, we would need, because this point here, the simulation sees it as floating because it has no ground reference. It cannot calculate the potential here. Let us add a really, really big resistor here. 1 mega ohm resistor added here, so this has no leakage current going through it. Okay, and this is how it looks. We put a 1 volt input signal and we get a 250 millivolt output signal. So this is exactly dividing the signal in two. Okay, one last thing before we close the simulation part is I believe it's important that we also discuss the filtering capability of a capacitor. This is 90% of the time you will use capacitors for filtering. Um, so the capacitor is really good at filtering noisy signal. Like this 12 volt line here, this is quite clean, so we can have a look here. This is oh, this is switching on, but we can look here. This is clean 12 volts, so we can zoom in. There is no ripple whatsoever on the signal. But if we take this line here where we have the 250 milliamps because we divided the signal in two, if we take this signal here, we can add it to our signal from this power supply. So let's go right ahead and do this. And now let's run the simulation and see how this signal is looking here. So we can see, yeah, beautiful. So we can see here, this is the bad ripple. We have here a 250 millivolt ripple, and you can see here after the capacitor is added, you have like, I don't know, this is 50, 20 millivolt ripple here. So this is not even, it's this is um, this is many times higher than the output ripple. Okay, and this is how we use the capacitors to filters. We want here on the output, we want clean signals, very little ripple, stable voltage levels, and on the input here being a noisy input, yeah, we need to filter this. Always filter the signal to be as clean as possible. With that being said, hopefully you have learned something new today. I would like to thank you for your time and looking forward to many more videos together. Wish everybody a great day.